Okay, we're going to talk about the final fundamental theorem of calculus. So what I'm going to do in this first video is I'm going to review the 2D situation for the divergence theorem. Because I think the 2D situation is a lot easier to draw and conceptualize, and a lot of these ideas extrapolate to the 3D situation. So if you find something in the 3D situation strange, just think back to the 2D and it'll make a lot more sense. So let's recall what I actually mean by this divergence theorem. It's really the second Green's theorem. And by second, I mean this version. It looks sort of like this. It was px plus qy, and this was equal to some integral of f dot n ds. And this was in contrast to the original versions of Green's theorem. You can call it the first version. And really, this is like the Stokes version, where it looks more like this. It's very similar. Qx minus py. Q and p are interchanged, and there's a sign difference. And as a result of that, what ends up happening is f, it's projected against the tangent vector, or we just call this thing dr. And so the only difference, of course, is that we just there was only a sign difference, and it was, I think we did p. We replaced that with minus q, and we just replaced q with p, and so these things are really the same. So they have the same identity, but the interpretation is different. Px plus qy is the divergence. We call this the divergence of f. And this thing has the physical interpretation of it's the inflow rate if you think of f as a velocity field. And the reason for that, I'm just reviewing. I'll link to the video in the description where I covered this stuff in more depth. I'm just giving a sketch to jog your memory. If you think about f as kind of a velocity field, and you had this normal vector, then this picture shows that there's actually a large outflow rate, and it corresponds to that dot product being large, whereas if you contrast it with the dot product being small, it looks like this. Where you have trapping. And notice how that dot product, f dot n, is actually 0 in this case. So the fluid, if you think of it as a velocity field, is trapped. So that gives an explanation for why we think of divergence as an accumulation, or conversely, it was negative dissipation rate. You could also think of it as outflow or inflow. And you can also think of it as a source or a sink. And what you'll see is the word flux is used to measure the integral of this on the boundary. Like if there's a if if this surface integral or this line integral in 2D, if it's large, there's a large outflux, for example. So the same ideas work in 3D, really. Right? Because in 2D, what is the divergence? Well, if you just think of F, well, F is PQR, right? And our position vector of independent variables, it's x, y, z. Really, you can think of this, these first terms, it's really just the x and the x. It's the first components, and it's also the y and the y, right? So naturally, if we put the z and the z together, we have RZ. That's what we have for our three-dimensional version of divergence. I'm just reviewing this. And so really, it's very similar idea in 3D. And so in 3D, there will be a similar Green's type theorem, rather second Green's type theorem. And the divergence has the same interpretation. Sources, sinks, outflow, inflow. And the integral of the divergence will be called the flux. And it will be equal to a boundary integral times the normal vector, whereas this will be a volume integral. And so this is just the heuristic idea of what's going on. So I wouldn't worry too much about having to learn anything supremely new in 3D. Let's get on to the next video.